Here's a puzzle that sounds almost trivial. Take a square, any square, a unit square will do, and try to cut it into triangles of exactly equal area. Start with 2 triangles, easy, slice along the diagonal. Try 4, also easy, 4 quarter triangles meeting in the middle. 6, 8, 10, any even count, no trouble at all, you can always do it. Now try 3 equal triangles, go ahead. Spend a minute. Draw squares, draw cuts, try to get 3 triangles that each cover exactly 1/3 of the area. You'll find yourself making one triangle too big, the next too small, adjusting, sliding vertices, squeezing a line, and somehow, it never quite works. Try 5, try 7, try any odd number at all. It doesn't work either. No matter how cleverly you cut, no matter how weirdly you place the vertices, you cannot dissect a square into an odd number of equal area triangles. Not 3, not 5, not 101. This is Monsky's theorem, proven by Paul Monsky in 1970. And what makes it beautiful isn't just the statement, it's the proof. A proof that reaches, unexpectedly, into the world of 2-adic numbers, borrows an idea from combinatorics, and closes the trap with an impossible lower bound. Let me show you how it works. You might think the obvious attack is brute force. Parameterize every possible way to cut a square into n triangles. Write down the equal area condition as a system of equations. Show the system has no solution when n is odd. The trouble is that the space of possible dissections is absurdly large. Vertex can sit anywhere. Edges can be almost anything. For each n, there are infinitely many topologically distinct dissections, and within each type a continuous family of positions. You can't just check them all, so the search is for something else. Not a proof by exhaustion, a proof by obstruction. We want a quantity, an invariant, that every equal area dissection of a square must satisfy. An invariant so restrictive that when the triangle count is odd, it flat out refuses to exist. Most invariants were used to come from algebra, areas, angles, sums of coordinates. These are all real numbers, and the real numbers are generous. They say yes to almost everything. What Monsky realized is that we need an invariant that lives outside the real numbers. Something with a different notion of size, one that sees hidden structure the reals smooth over. And we need combinatorial structure too, a way to talk about vertices and colors and neighbors, something that can count parity, odd versus even, without caring about the exact geometry. The tool for that, as you might have guessed, is a 2-dimensional analog of a very old counting argument. Let's start there. Imagine we take the unit square and paint every single point in the plane one of 3 colors. Call the colors A, B, C. The specific rule will come later. For now, just imagine the coloring is fixed, given to us from above, and every point in the plane has a color. Some triangles will be boring, all 3 vertices the same color, or 2 vertices the same and 1 different. What's interesting is a rainbow triangle, 1 vertex of each color, 1 A, 1 B, 1 C. These are the rare beasts. Here's the idea. We're going to invent a coloring of the plane so that at least 1 triangle in any dissection must be a rainbow, and so that any rainbow triangle carries a peculiar numerical property that odd triangle counts can't satisfy. Before we design the coloring, look at what the rule already tells us combinatorially. The corners of the unit square, bottom left, bottom right, top left, will be forced to carry specific colors. Under our upcoming rule, those corners go A, B, B, C. All 3 colors appear around the boundary. On the bottom edge of the square, only colors A and B will appear. On the left edge, only A and C. On the top edge, B and C. On the right edge, B and C. Notice the pattern. Each edge sees exactly 2 of the 3 colors, and the transitions between them are forced by the corners. This kind of boundary condition, colors constrained on the edges, forced combinations on the vertices, is the setup for a classical counting lemma. The lemma is almost 100 years old. It's Sperner's lemma, and it tells us something surprising about how often rainbow triangles must appear. Emanuel Sperner stated his lemma in 1928. It's one of those results that sounds obvious once you see it, but in 2 dimensions, it's the engine behind some of the deepest theorems in topology, including Brewer's fixed-point theorem. Let me show you the easy one-dimensional case first. Take a line segment, paint the left endpoint A, paint the right endpoint B. Subdivide the segment into tiny pieces and color each interior division point either A or B, however you like. Now count the subsegments whose endpoints are different, 1A and 1B. I claim this count is always odd. Here's why. Walk along the segment from left to right. Every time you cross from A to B, you add 1. Every time you cross from B to A, you add 1. You start in A land, you end in B land, so the total number of crossings must be odd. That's the lemma. Now the 2-dimensional version. Take any triangulated polygon. Color the vertices A, B, or C with boundary constraints. On each edge of the outer polygon, only 2 colors appear, matching the one-dimensional rule. Sperner's lemma says the number of rainbow triangles with 1A, 1B, and 1C, is odd. In particular, it's at least 1. The proof is a beautiful 2-dimensional door-counting argument. Mark every edge of every triangle that has an A on one end and a B on the other. Call these AB edges. For each small triangle, count how many AB edges it has on its boundary. A rainbow ABC triangle has exactly 1. A triangle colored ABB or AAB has exactly 2. Anything else has 0. Now add that count over all triangles. Interior AB edges are shared between 2 triangles, so they contribute 2 each. Boundary AB edges contribute 1. From the one-dimensional lemma applied to the bottom edge, the boundary contribution is odd, so the total count, twice the interior plus the boundary, is odd. But it also equals the rainbow count plus twice the double-colored count, so the rainbow count must itself be odd. That gives us at least 1 rainbow triangle, and it will turn out to be exactly the triangle we need. To build the coloring, we need a very strange tool from number theory, a way to measure numbers that isn't the ordinary absolute value. It's called the 2-adic valuation. For a non-zero integer, the 2-adic valuation is easy. Count how many times you can divide the integer by 2 before it becomes odd. That count is its 2-adic valuation. 8 has valuation 3. Divide by 2 by 2 by 2 and you get 1. 12 has valuation 2. 17 has valuation 0. 0 itself is defined to have valuation infinity because it's divisible by 2 forever. We also define the 2-adic size, 2 to the minus valuation. Small valuation means big size. Big valuation means small size. So odd integers all have 2-adic size 1. 2 has 2-adic size 1/2. 4 has size 1/4. In this new geometry, highly even numbers are tiny. For a rational number p over q, we extend the definition. The valuation of the fraction is the valuation of the top minus the valuation of the bottom. So 3/2 has valuation -1, size 2. 5 over 16 has valuation -4, size 16. Rationals with big powers of 2 in the denominator become enormous. Here's the crucial property. The 2-adic size respects multiplication. The size of a product equals the product of sizes, and it satisfies a sharp triangle inequality. The size of a sum is at most the larger of the 2 sizes. These rules turn the rationals into a geometry where numbers cluster by their divisibility, not by their magnitude. Now for the heavy move. We want to extend this size function, this 2-adic valuation, from the rationals to all real numbers, because the triangles in our dissection can have vertices with irrational coordinates, not just rational ones. And extending a valuation to the full real line requires, I won't hide it from you, Zorn's lemma, a form of the axiom of choice. Mathematicians have proven this extension exists. Every real number gets a 2-adic size. The rules, multiplicativity, the sharp triangle inequality, agreement with the original definition on rational numbers, still hold. Beyond those rules, the extension is weird and non-canonical. But we don't need to look at it directly. We only need to use its rules. With this tool in hand, we can finally design the coloring. Here's the rule. For any point in the plane with coordinates x and y, we look at the two adic sizes of x and y. We compare them to each other and to 1. If both sizes are less than 1, meaning both coordinates are too adically small, paint the point color A. Otherwise, if the size of x is at least 1 and is bigger than or equal to the size of y, paint the point color B. This is the region where x is too adically large and dominates. Otherwise, the size of y must be at least 1 and strictly larger than the size of x. Paint the point color C. Every point in the plane gets exactly one color under this rule. Let me check the four corners of the unit square. The origin, 0, 0, has both coordinates equal to 0, which we treat as having two adic size 0, the smallest possible. Both sizes are less than 1, color A. The bottom right corner is 1, 0. The size of 1 is 1, the size of 0 is 0, so x dominates at size 1. Color B. The top right corner is 1, 1. Both coordinates have size 1. They're tied, and the rule breaks the tie in favor of x. Color B. The top left corner is 0, 1. Now y dominates at size 1. Color C. So going around the boundary of the unit square, the four corners carry colors A, B, B, C. All three colors appear, check. Now look at each edge. The bottom edge connects A to B, so only A and B appear there. The left edge connects A to C, so only A and C. The top edge connects B to C. The right edge connects B to C. Every edge sees exactly two colors, and every corner combines the two edges meeting at it. Sperner's setup. Exactly. Now the decisive step. Take any triangle with vertices at 3 points in the plane. The area is given by the shoelace formula. Half the absolute value of a 2x2 determinant in the differences of the coordinates. Specifically, if the three vertices are P, Q, and R, the area equals 1/2 times the absolute value of the determinant whose rows are Q minus P and R minus P. It's a classical formula from analytic geometry. Now take its two adic size. The two adic size of the area equals the two adic size of 1/2. In the two adic sense, that's size 2. Times the two adic size of that determinant. So the two adic size of the triangle's area is twice the two adic size of the determinant. The lemma we need is this. If the triangle is a rainbow, vertices of all three colors, then the two adic size of the determinant is at least 1. That forces the two adic size of the triangle's area to be at least 2. Why does the determinant have size at least 1 for rainbow triangles? Because of the way the colors were defined. Each color constrains the two adic sizes of the vertex coordinates. When you expand the 2x2 determinant as a sum of products and apply the sharp triangle inequality along with multiplicativity, the two adic size of each term is at most 1, but one of those terms, pinned by the rainbow coloring, has size exactly 1. So the whole determinant has two adic size 1 or larger. This is the heart of the proof. The rainbow coloring forces a specific two adic lower bound on the determinant, which in turn forces the two adic area to be at least 2. Now the closing move. Suppose we've dissected the unit square into n equal triangles. Each triangle has area 1 over n. Sperner's lemma tells us at least one triangle is a rainbow. For that rainbow triangle, the two adic size of its area, that is the two adic size of 1 over n, must be at least 2. The two adic size of 1 over n is 2 raised to the two adic valuation of n. So 2 to that valuation is at least 2, which means the valuation of n is at least 1, which means n itself is divisible by 2. N must be even. There are no equal area dissections of the unit square into an odd number of triangles. Never. For any odd n. The theorem is done. Paul Monsky published this argument in 1970 in a short paper in the American Mathematical Monthly. He credited his colleague Fred Richman with raising the question, and the proof, compressing two adic valuations, Sperner's lemma, and a determinant bound into 2 pages, has become a model of mathematical economy. Since then, the result has been generalized in every direction you'd expect. You can replace the square with other polygons and ask, for which n can this polygon be dissected into n equal area triangles? Regular hexagons, kites, trapezoids. The answers involve new 2-adic and 3-adic obstructions that mirror Monsky's original idea. In higher dimensions, there are analogues for cubes and simplices, proven with higher dimensional Sperner arguments. The theorem has also quietly reshaped how we think about dissection problems in general. Whenever a geometric problem looks like it wants a combinatorial or measure-theoretic invariant, and none of the usual ones work, someone tries a p-adic valuation, and often it works. Monsky gave mathematicians a new kind of eye. If you enjoyed this, the original paper, 2 pages, is a good way to see the full proof in its native form. If there's a theorem you'd like to see next, drop it in the comments. And if this video helped you see why a problem can be impossible in a beautiful way, consider subscribing. Thanks for watching.